Okay, well, we're live, so let's get going. Today we're going to look at uncertainty and what to do with it in A-level physics. So, let's just dive in then. I have to say, this is one of the most boring parts of A-level physics, but it's also, believe it or not, really important. There are lots of stories told of physics discoveries and physics practicals. They didn't really work because they didn't take into account their uncertainties correctly. So a classic example would be the story recently when a group of physicists claimed to have discovered that they got a particle travelling faster than the speed of light, and this went all around the media and all around the world, and lots of labs were trying to reproduce this, and in the end it came down to something was wrong with one of their bits of equipment, hadn't calibrated it properly, and that was because they hadn't taken account of their uncertainties correctly. So this is important stuff. So today we're going to look at what exactly it means when we talk about combining uncertainties. That's the kind of the main thing. How to deal with that really common exam question, and as part of that, we're going to be focusing on this idea of absolute and percentage uncertainties and what to do with them when you stick them into formulas. Which, yeah, there we go. So that's what we're going to do. So without further ado, we'll jump in. So first of all, we're just going to look very briefly at this idea of a ruler. It's going to crop up a lot today. This is part of a ruler. It's just measuring centimeters along there. So that's kind of nothing unlikely here. So how long is this line? Well, you can clearly see that it's gone past 15 centimeters and 0.1, 0.2. It's not exactly at 0.3, but it's kind of close to it. So, to all intents and purposes, we can't say anything other than that this is 15.3 with a little bit of uncertainty on that reading, because is it 15.28, 29? What is it? 15 point what? So we call it 15.3 because that's the nearest one. So we'll say this is 15.3 with a bit of uncertainty. Now that uncertainty, when you're taking a single reading like this, is generally speaking always half of the smallest kind of reading that you've got on your measuring instrument, which in this case is 1 millimeter. So in other words, it's half of a millimeter. Now the ruler, being a ruler, is in centimeters, so we want to express our error or our uncertainty as half a millimeter, but in centimeters. So that's going to be 0.05 centimeters. So this is the size of our reading. This line, then, we can best say that it's going to be 15.3 plus or minus 0.05 centimeters. Now, when you think about it, this is around about 20. Well, it is in actual fact a 20th of a millimeter, and that kind of makes sense because a 20th of a millimeter would be half of a 10th of a millimeter, which is the smallest resolution. All right, so that's good. Now, this is known as absolute uncertainty, and the reason it's called absolute uncertainty is because basically I always think when I teach this, I say it's because it's got a unit. And every time you take a reading, I was trying to think of a case when you take a reading where it isn't an absolute uncertainty, because every time you use a piece of kit to take a reading, you're going to measure a quantity, volts, length, mass, whatever it is, and so it's always going to have a unit, so it's always going to be an absolute figure. So when you take a reading, you get an absolute figure. Now, what can be very useful, in fact essential, is to be able to convert this into a percentage, which is the other type of uncertainty. So this is the absolute uncertainty, and to convert it into percentage is really extremely simple. You just take the value of the uncertainty, which in this case is 0.05, and divide it by 15.3 and then times it by 100. I mean, really, what could be easier than that? And that will turn it into a percentage. Now, if you do that, in this case, it's going to come out as equaling, oops, let's get my pen to work. For some reason my pen died. Right, it's back now. That's going to equal 0.33%. So in other words, we can say that this reading is also could be written as 15.3 plus or minus 0.33%. In other words, 0.33% of the actual value. So that's the percentage uncertainty, and you need to be really good at just going backwards and forwards between the two. All right, which is obviously not that difficult. Just take care with your significant figures here. So I've stuck this to 2 significant figures because that's 2 significant figures. You might want to make a case I could go to 3 because of that, but the error itself is in 2, so I stuck to 2. Okay, one thing that's worth pointing out at this point, that when you do your degree in physics, and I remember that we would do 2 or 3 hours to do a practical and then a day to work out the uncertainties. It was seriously that complicated, and I began to think that really uncertainty is closer to an art than it is to a science, and people disagree about how you should do it in particular circumstances, but that's not really going to crop up at A level, that sort of stuff. It's pretty straightforward. Now let's get into business. Remember, the aim of this video is how do you combine these things when you're doing calculations. Well, most calculations that you'll ever do can be broken down to doing 4 operations. So adding, taking away, or subtracting, I suppose we could say. I've just noticed this isn't fitting too good in the screen, so what we'll do is we'll just reduce that a little bit. Try again, still not fitting too good. So just a little bit of housekeeping here. Let's just move that a little bit. Maybe make that a little bit bigger, and there we go. So I hope that hasn't spoilt your enjoyment too much. Let's we'll carry on now. We're back to where we were. Just lock that down. Right, so basically there are 4 operators, as you know, in maths: adding, subtracting, timesing, and dividing. And there are 2 or 3 rules when you are dealing with uncertainties that you just have to learn. The first is, I've called it adding, but I suppose you might want to put or subtracting. But then again, what is subtracting? It's just adding a negative number, isn't it? So really, it's just adding. And the rule is that when you're going to add uncertainties, you have to use absolutes. So you just got to remember that, absolute uncertainties. So not percentages. You have to use absolute. So maybe the best way to think about this is to take an example. You'll see what I mean. So now we'll go back to our ruler. What we're going to do is think about how long is that line there. And so we have our 15.3 plus or minus 0.5. And what about the other end? Well, the other end is going to be 10.1. It's about 10.2. So we're going to say 10.2 plus or minus the same absolute uncertainty, 0.05. So in order to work out the actual length of this line, it's really straightforward, isn't it? We just take one end and take away the other end. So we're going to do 15.3 take away 10.2, and dead simple, isn't it? And as you know, that's going to come out as 5.1. But what do you do with the uncertainties? Well, you know the uncertainty on each of the ends is 0.5. You also know the rule from previously that when you're dealing with adding or subtracting, you use the absolutes and you add them. It doesn't matter if you're taking away or adding numbers together, you always add the absolute uncertainties. So coming back to our ruler then, we're going to take the uncertainty on the 15.3 and add it to the uncertainty on the 10.2, which is really 0.05 plus 0.05 again. So in other words, the value is 5.1 plus or minus 0.1 centimeters, and that would be, that's your first calculation in a way, or at least the first one with me, I suppose I should say, this afternoon doing this little live stream. So 5.1 plus or minus 0.1 centimeters. So the rule, when you're adding or subtracting, you just absolute errors, add them. Okay, so that's the first bit. So let's move into the multiplications now. This time the rule is very similar. Remember, dividing, really, when you're dividing something, what you're doing when you're dividing is you're just multiplying by 1 over the thing. So we just put multiplication, although really I suppose, to be totally right, you might want to write division as well, but they're the same thing. So the rule for this time is, this time we take the errors and we add together the percentage uncertainties. See, when I was doing physics, they weren't called uncertainties, they were called errors. And so I have to correct myself. Every time I teach this stuff, I have to keep correcting myself because I say percentage errors. That's just how it comes out. I mean uncertainties. It's kind of the same thing. Uncertainties is actually a better word for it, I think. in retrospect. So the rule here, if you're going to multiply percent errors together, when you multiply two figures, you take their percentage errors and you add them up. So let's take a really simple example of this and see where we go. So in this example, I have a voltage of 6 volts plus or minus 0.2 volts. So notice that's an absolute. It's got a unit there, absolute error, and a current of 0.52 amps, again plus or minus an absolute of 0.4. And you've got to find the resistance. Well, you know how to find the resistance. You just divide the two numbers. So voltage, resistance is voltage over current. So we just do 6.0 over 0.52, which will give us a resistance of 1.2 ohms. Well, plus or minus what? Well, in order to do this, you have to convert both of the uncertainties here into percentages. So it's literally just donkey work going through that little calculation that we did at the start. So let's convert the voltage first. It's going to be 0.2 divided by 6.0 times 100. When you do that, you get 3.3%. Do the same thing for the current. It's going to be 0.04 over 0.52 multiplied by 100. It's going to be 7.7. So the total error on the value of our resistance is going to be 3.3 plus 7.7, which I'm sure you can see is going to be 11. So our answer for the resistance then is 1.2 ohms plus or minus 11%. Now you can see that's beginning, 11%, that's beginning to get quite significant. So just call it 10. So in other words, we're out. There's an uncertainty of 10% either way on that figure of 1.2. Now you might in an exam state now have to convert this 11% back to an absolute value. So you would just do 1.2 times 11 over 100. And that would now be whatever that comes out as. That would be your absolute value that you could put in. Okay, so that's what you do when you're doing multiplications. In a moment, we're going to look at some examples of how you use these in a couple of actual exam questions, which I guess in some ways will be the most useful thing. So far then we've looked at what you do when you add or subtract, use the absolute values. What you do when you multiply or divide, use percentage values. But the last is what you do when you've got powers. So we've got the figure y to the power of something. So it could be r cubed, or I don't know. Yeah, r cubed's a good one, isn't it? Radius cubed to get the volume. So what you do with this, it's really straightforward. You take the percentage error and you times it by n. So you have best way is to think of an example really. So suppose we had a value. So for this we take percentage errors times boop, 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 by n. So if we have a figure like well, let's do an example. Suppose we have a radius of 5.2 centimeters plus or minus 0.1 centimeter. Again, notice it's an absolute value. So the first thing you've got to do with that is convert it to a percent. So 5.2 plus or minus 0.1. You see how tedious this gets. You know, you're probably thinking, oh, let's fast forward this. I've seen this 5 times already. And that's what doing this stuff is like. It's over and over. It's almost relentless. You just got so many opportunities to press the wrong button on your calculator or add something when you should be multiplying or whatever. It's really simple. Anyway, this comes out as a little diversion there. This comes out as 1.9%. So that's the value of our radius with the percentage error. So now it's really just a question of cubing everything, because we want to know what is the error on r cubed, the radius cubed, the volume in other words. So we take 5.2 and we cube that. Then it'll be plus or minus the 1.9% that we just worked out, and then you bring the power, which in this case is 3, and stick that down the front. So you can see this is nearly 6%. It's going to be 5.7%, isn't it? So 5.2 cubed, whatever that is, I mean it's going to be 125-ish, 130, plus or minus around about 7%. Let's call it 5.7%, I think. you might want to check that, but that's the idea. So you bring the power down and then you multiply by that power. So those are the 3 rules. If you assiduously just use those every time, I want to say you can't go wrong. But whether that's true is obviously up to you. You can go wrong, of course, but that's a good place to start, is just to think these 3 rules, do them over again. Another thing that's worth saying here is that although this stuff is boring, it's easy marks, as you'll see in a minute when I get to the questions. But really, if you do lots of practical work at school, which of course is arguable, what you find is you do this over and over again and it becomes second nature. But when I'm tutoring students, I find that many of them never really deal with this until just a few weeks before their exam. So they did it right at the start, year 12, and then they get to the end of year 13 and, oh, flipping hell, I've got to remember this and I don't get it. So I spend a lot of time going over this stuff, which is why I thought, let's get this live stream out of the way and do it early on, and hopefully that will be useful. So here we have a multiple guess question, I think, from some paper somewhere. I can't remember exactly where. And we have the diagram shows the reading on a voltmeter at one instant. So this is going to be moving around, okay? And the manufacturer says that we have a reading plus or minus 2%. So really what we've got going on here is 2.39 plus or minus 2%. And it says calculate the absolute uncertainty. And you'll see it's only 1 mark, which kind of tells you that it's pretty straightforward, really. At least that's the theory. So what we do then is we just need to work out what is 2% of our value here, and it's not that difficult. So we're going to do pen's gone again. I wonder why it does that. 2.39 times 2 over 100, because obviously that's 2%, isn't it? Which is going to be equal to 0.0478. And we just can't justify these sig figures, but I'll put them there for the moment. So this means that our answer is going to be 2.39 plus or minus 0.0478. We can't justify that, so we'll go to 0.05 volts. Alright, so that will be the answer there. 5/50 of a volt. Right, okay, so no, 500ths of a volt. 5 centivolts. I got that wrong. But anyway, it's 0.05. So that's the first one. Here's another example. This is a little more complicated. Again, it's a multiple guess. So this time we have a question that says we've got values here for tension, length, and mass per unit length. So mass per unit length, which is normally written as mu, Greek letter mu, like this, mu, mass per unit length, of a string stretched between 2 support. And we've got some percentage uncertainties here. Notice their percentages. And a stationary wave is formed on the string. What is the percentage uncertainty in the calculated value? Well, perhaps you haven't done this stuff yet, but in a way it doesn't matter. I'll just give you the formula that you would use. This one is on the formula sheet, and this is a really good example, this question, of what you do when you're going to combine percentages. Okay, so that's the formula. So we can look at this and we can say, I'm going to break this into like 2 sections. So we'll think about this one, and then we'll think about the other one, the second bit here. So if we can get the percentage errors on those 2 bits, we can just add them together. So let's think about the 1 over 2L. So 1 over 2L. What's the percentage error on 2? Good question. Well, it's a constant. It's a number. So it has no percentage error. Now remember that even though it says times 2 times L, because we're looking at the percentages, we're going to add them. So take the length, it's 0.8. So we're doing 0% plus 0.8%, like this. And it's 1 over that. Now when we divide, we just take the error on the top and divide it by the error on the bottom. Well, the error on the top is also 0 because it's just a number, or it's a perfect number, I suppose I should say. Therefore, the percentage error of this lot is just simply going to be 1 over, or 0, we've got 0 on top here, over 0 plus 0.8. 0.8%. Now remember, this, although it looks like it's dividing, we're talking about the percentage errors. When you divide, you just add them. So we have to add all these together, which of course just comes out as 0.8%. So the error on this, the bit that's in the blue circle there at the start of the equation, is just 0.8%. Okay, so that looks complicated, but it isn't. So let's deal with the other part now. What about the, let's put a little divide there. What about the root period, or tension I should say, tension over mass per unit length? Well, another way to write that, of course, is just to think of the power that we have. So this will be equal to T over mu all to the power of a half. Power rule, we know what to do with that. So let's break this down. For the tension, we have a percentage of 4%. For mass per unit length, it's 2. So we always do what's in the bracket first. And remember, we're dividing the percentages. So in this case, because we're dealing with the percentage errors, we just add them. So now we can say that 4 plus 2, well, 6, isn't it? So now we have 6% error or uncertainty. See what I'm doing there? Raised to the power of half. So when we've got an index or raised to a power, we just bring that power down and multiply. So this is going to become a half times 6. Sorry, thinking ahead. Half times 6%, which is obviously 3%. So that means the second part of our equation up there is 3%. Now these two sections of my equation are multiplied together, so we just add those percentages. So the total error here then is going to be equal to 3 plus 0.8, 3.8%. So this one is B. Now, that might look like a complex question, but if you know what you're doing, if you're solid about which rules you have to use, it's not that difficult at all, really. Okay, so I've got one more question. Let's just take a look in the chat. No questions yet. So I should say I'm going to be doing this. My plan is to do this regularly at this spot every week. I'm going to keep this session clear so that I can really get into these, these live streams, because I found that they do build my channel. They are slow but steady when I like that. So good. Anyway, last one then. So this is a good question. I like this one. So it's another multiple guess. And this time we're looking at finding the resistivity. Again, you might not have covered this yet, so just bear with. We're going to use this equation that the resistance of a piece of metal is this strange thing times L divided by A. So it's the length. So imagine a bit of wire like this. It's the length of the wire times the cross-sectional area of the wire, multiplied here by this thing called resistivity. So again, this is a Greek letter, sometimes written as rho, R-H-O, or just R-O, rho anyway, or even R-O-E, it's different ways. But it's a Greek letter, and it's a Greek letter rho, and it's the resistivity. And we are trying to determine this, so this is what we're after. And a student goes ahead and takes readings. It says she determines the resistance by measuring potential difference, voltage, across a wire and the current through it. So we could just say that we know that from Ohm's law, V is IR, so V over I equals R. So that means we can substitute in here, we can write this as just V over I. So now we've got to the point of saying V over I equals rho L over A. Now remember what we're after. We need to know what is going to be the percentage error on rho. So we're going to rearrange this equation. So multiply both sides by A and divide both sides by L. So that will give us VA over IL equals the resistivity, which is what we want. Now there's one more problem here. And the problem is that, and this is such a common question, I can't tell you how often this comes up. We want to know this resistance and we have to use the cross-sectional area. And it's always, if it's a wire, it's just a circle. And our student here is measuring the diameter. Now to get the area, you have to square that diameter. We actually square the diameter over 2 because that'll be the radius and you square it. So in actual fact, the area is going to be equal to the resistivity is going to be voltage times 2 pi r squared over IL. Now, let's go through. The question asks us if each of our quantities has 1% on it, which makes the biggest difference to the calculated value of the resistivity or the uncertainty. Remember, for the resistivity, for multiplying, we just add the percentage errors. So, let's go through. We have 1% for V. We have 1% for R. We have 1% for I and 1% for L. Now, all we're doing is multiplying and dividing here. So we can just add them all together. So you would think that this would be 4%. But of course it isn't, because I haven't taken account of the square. We have to put a 2 down there so that this error on R squared is actually 2%, which means that this is 5%. So which of the 4 quantities has made the biggest impact on this percentage error? Well, it's actually the resistance, isn't it? Because it's squared. So it's, sorry, I didn't mean that. I meant the diameter or the radius, because we have to square its value. So its error is 2% rather than 1%. So the answer to this one is B. Now, when you've been doing physics a bit longer, you can just look at this and you can say, is there anything in this equation that's got a square? Well, resistance doesn't have a square. Rho doesn't have a square. L doesn't, but area does, because diameter. Pi 2, what am I talking? It's pi r squared, isn't it? I made a little error here. It's pi r squared. So those of you that are on the ball will notice there's a small teacher error here, which is this 2. It doesn't actually make any difference to the answer. It's pi r squared, not 2 pi r squared. All right. Anyway, so that's the answer to that. So take out for today. Learn those 3 rules: when to use absolute, when to use the percentage, and what to do with the powers. Now, in another video, I might cover how you use actual bits of kit. So in the start of this video today, we just talked a little bit about using a ruler. How exciting. But what do you do if you're using a micrometer, or you're using balances, or some other piece of exciting equipment that you might come across? So don't forget to check out loads and loads and loads and loads of my other videos, and hope that was useful. And thanks for watching. Don't forget, same time, same